1.5 million kilometers from Earth, a telescope saw something impossible. Tiny red dots scattered across the darkness, objects that should not exist. Scientists stared at the images for 2 years, searching for answers. What they found changes everything we thought we knew about black holes, galaxy formation, and the violent birth of our universe. These are not distant stars. They are monsters wrapped in fire, caught devouring their surroundings in the most extreme feeding frenzy ever recorded. If you enjoy mysteries at the edge of space, like and subscribe, take a breath. We are about to witness creation itself. December 2021, the James Webb Space Telescope opened its eyes for the first time. Scientists expected to see galaxies. They expected stars forming in distant clouds. They expected to map the early universe with unprecedented clarity. What they got instead was a puzzle wrapped in crimson light. Scattered among the familiar cosmic landscape were tiny points of red, not stars, not galaxies behaving as models predicted. These objects glowed with a color that made no sense. They appeared in places where nothing should shine that brightly, that strangely. Researchers at the Niels Bohr Institute examined the data, then examined it again. The red dots appeared during a specific window of cosmic time, when the universe was only a few 100 million years old. Think of it like this. If the universe's entire history were compressed into 1 year, these dots showed up in early January. By late February, they vanished completely. That disappearance raised the first alarm. Objects in space do not simply blink out of existence on cosmic timescales. They evolve, they merge, they fade slowly over billions of years. But these red dots followed a different pattern entirely. The color itself presented another mystery. Light shifts toward red when traveling across vast distances due to the expansion of space. Astronomers account for this. They can calculate what an object should look like after its light journeys for 13 billion years, as it was billions of years ago. The telescope's mirror spans more than 21 feet across, made of 18 hexagonal segments coated in gold. Gold reflects infrared light better than any other metal. Each segment can be individually adjusted by motors, so precise they can move the mirror by distances smaller than a wavelength of light. This precision allows Webb to focus on objects so distant that their light has been traveling since the universe was an infant. When Webb captures an image, it is not photographing the present. Light takes time to travel. The farther away an object sits, the older the light we receive from it. Those red dots appeared in images showing the universe as it existed just 700 million years after the Big Bang. We are literally looking back in time, witnessing events that unfolded when the cosmos was barely 5% of its current age. That is why Webb's discovery carries such weight. These objects existed during a period scientists call the cosmic dawn, when the first stars ignited and the first galaxies began to form. Whatever those red dots are, they were present at creation's earliest moments, and their presence there changes everything we thought we understood. 700 million years after the Big Bang, the universe was unrecognizable. No planets existed yet, no life, no complex chemistry. The cosmos had just emerged from what astronomers call the Dark Ages, a period when no stars had formed and the entire universe sat in complete blackness. Then came light. The first stars ignited, burning blue-white and massive. They lived fast and died violently, exploding as supernovas within a few million years. Their deaths scattered heavier elements into space, the raw materials needed for everything that would come after. The temperature of space itself was warmer then, not by much in human terms, but enough to change how matter behaved. The cosmic microwave background radiation, the afterglow of the Big Bang, still filled every corner of existence with a faint heat. Gravity had been pulling matter together for hundreds of millions of years. Small clumps grew into larger ones. Dense pockets of gas collapsed under their own weight. Where conditions aligned perfectly, stars formed in clusters. These clusters would eventually become the first galaxies. But galaxies were rare. The ones that did exist were small, chaotic, and violent. Massive stars formed and exploded in rapid succession. Gas clouds collided and merged. Black holes began to appear, feeding on the abundant material around them. The space between these early structures was different too. Dark matter, the invisible substance that makes up most of the universe's mass, had not yet organized into the vast cosmic web we see today. Instead, it formed loose filaments and knots, channels through which normal matter could flow and concentrate. Imagine a city under construction, not the finished metropolis with organized streets and buildings, but the early phase when foundations are being laid and structures rise from bare earth. That was the universe at 700 million years old, raw, unfinished, changing rapidly. Light traveled more freely then. The universe had recently undergone reionization, a process where radiation from the first stars stripped electrons from hydrogen atoms. This made space transparent to certain wavelengths of light. Before reionization, the universe was opaque, like fog. After, it became clear, allowing light to travel across vast distances. This is the era Webb can observe. When it looks back 13 billion years, it sees light that left objects during this tumultuous period. Every photon that reaches the telescope carried information from that time, encoded in wavelength, intensity, and direction. Those red dots appeared during this cosmic construction phase. They existed when the universe was building its first major structures. Whatever they are, they played a role in shaping what came after. Scientists can measure the age of the universe when these objects emitted their light by examining how much space has expanded since then. Light stretches as space expands, shifting toward longer, redder wavelengths. By measuring this redshift, astronomers can calculate exactly when in cosmic history the light began its journey. The red dots show a redshift corresponding to 700 million years after the Big Bang. They existed at a time when everything was still being figured out. When the rules of how galaxies form, how black holes grow, and how structures evolve were being written in real time, what happens next depends on understanding what these crimson points of light actually are. Galaxies form slowly. That is the rule written in every astronomy textbook. Small clumps of gas and dark matter come together under gravity. Over millions of years, they accumulate more material. Stars begin to form. The proto-galaxy grows, merging with other small clumps. Eventually, after hundreds of millions of years, you get something recognizable as a galaxy. This process takes time because gravity, while persistent, moves matter gradually. Gas must cool enough to collapse. Stars must form in waves, each generation taking millions of years to live and die. Black holes grow by accumulating material bit by bit. The red dots violated every step of this timeline. First, they were too bright. An object's brightness depends on how much light it emits. To shine brightly enough to be detected across 13 billion light-years, these dots had to be generating enormous amounts of energy, the kind of energy output usually associated with mature, massive galaxies. But mature galaxies should not exist 700 million years after the Big Bang. There simply had not been enough time for them to form through normal processes. It would be like finding a full-grown oak tree in a forest that was planted yesterday. Second, the dots were too compact. Galaxies have size. They spread out over thousands of light years. These objects appeared as pinpoints, far smaller than any galaxy should be while still producing that much light. Third, their color defied explanation. Galaxies contain stars of different ages and temperatures. Young, hot stars burn blue. Older, cooler stars glow red. A typical galaxy shows a mix of colors blended together. These objects glowed almost pure red, suggesting something fundamentally different about their composition or the way they generated light. The spacing of the dots created another puzzle. They appeared scattered across the sky in numbers that suggested they were common. If hundreds of these objects existed in the tiny patch of space Webb observed, billions must exist across the entire universe at that time period. Common objects should fit known physics. Rare anomalies can sometimes be explained by unusual circumstances. But when something appears everywhere, it means the processes creating it are fundamental to how the universe works. Scientists tried to model galaxy formation to produce these objects. They adjusted the rate of star formation. They changed the amount of dark matter. They modified gas cooling rates. Nothing worked. Every model that created objects bright enough made them too large. Every model that kept them compact made them too dim. Some researchers proposed completely new types of stars. Maybe in the early universe, stars could form with compositions we have never observed. Perhaps they could burn hotter, brighter, and faster than current physics allows. Others suggested the dots were not galaxies at all, but something else entirely. Maybe clusters of primordial black holes. Maybe exotic dark matter interactions. Maybe phenomena we have no names for because we have never encountered them. The problem with proposing new physics is that it raises more questions than it answers. If stars could form differently in the early universe, why did they stop? If exotic processes occurred then, why do we see no trace of them now? Derek Watson and his team knew the answer had to be simpler. Nature tends toward elegance. When observations do not match theory, it usually means we are looking at familiar objects from an unfamiliar angle. They needed to think differently about what they were seeing. The breakthrough came when they stopped asking what kind of galaxy could produce this light and started asking what else in the universe glows red. The first explanation seemed logical on the surface. These red dots must be massive galaxies. Galaxies so large and so luminous that they could be detected across the entire observable universe. Galaxies that formed impossibly fast, breaking the rules but still fitting within the category of objects we understand. Astronomers had seen bright, distant galaxies before. Some of the earliest Webb observations revealed galaxies that appeared more massive than models predicted. If the universe could form a few impossibly large galaxies early, perhaps it could form hundreds of them. The theory gained traction because it required the least amount of new physics. Galaxies were known objects. We understood how they worked, at least in principle. Maybe the models just needed adjusting. Maybe star formation was more efficient in the early universe. Maybe dark matter clumped faster than simulations suggested. Researchers began calculating what these galaxies would need to look like. They would need stellar masses of billions of times our star's mass. They would need to have formed nearly all their stars within the first few 100 million years of cosmic history. They would need to be incredibly dense, packing all that mass into a small volume. The numbers started to fall apart almost immediately. To form that many stars that quickly, these galaxies would need gas infall rates that violated conservation of mass. Material would need to flow into them faster than gravity could pull it. They would need star formation efficiencies approaching 100%, meaning every single atom of gas turned into stars. In reality, star formation efficiency rarely exceeds 10%. Most gas gets blown away by radiation pressure or heated too much to collapse. Then came the color problem. Stars form in a range of masses. Small stars burn red and cool. Medium stars like our own burn yellow. Massive stars burn blue, white, and hot. A galaxy forming stars rapidly would have all types mixed together. Its light would appear white or blue-white, not red. To appear pure red, these galaxies would need to contain only old, cool stars. But old stars take billions of years to evolve from their hot, blue youth to their cool, red, old age. These galaxies existed when the universe was only 700 million years old. There had not been time for stars to age that way. Some scientists suggested the galaxies were full of dust. Dust absorbs blue light preferentially, making objects appear redder than they are. This works for nearby galaxies. But the amount of dust needed to redshift light this dramatically would need to be enormous. Where did all that dust come from? Dust forms from heavier elements created in dying stars. In the early universe, few stars had lived long enough to die and produce dust. Another issue emerged from the observations themselves. When Webb looked at the same patch of sky at different wavelengths, the red dots appeared strongest in specific infrared bands. Their spectrum, the rainbow of colors they emitted, had features that did not match stellar light. Stars emit light in a characteristic pattern based on their temperature. These objects emitted light in a pattern that looked different. The galaxy theory also could not explain why the red dots disappeared after a billion years. Galaxies do not vanish. They evolve, merge, and transform, but they remain visible for billions of years as they age. If these were galaxies from 700 million years after the Big Bang, we should see evolved versions of them at later times. We should be able to track their development. We cannot. The red dots appear only in a narrow window of cosmic time, then they are gone. By mid-2023, the impossible galaxy theory was crumbling. The evidence pointed elsewhere. Scientists needed a new explanation, one that accounted for the brightness, the color, the size, and the temporal window all at once. Watson's team started looking at the one type of object in the universe that could produce the right kind of light in the right colors with the right intensity. An object that grows rapidly, shines intensely, and can exist in a transient state before evolving into something else. A black hole. Science moves slower than headlines suggest. Between December 2021, when Webb first observed the red dots, and January 2026, when the answer was published, thousands of hours of work occurred. Not dramatic breakthroughs, not sudden revelations, just careful, methodical analysis of data. The team at the Cosmic Dawn Center started by cataloging every red dot Webb had detected. Hundreds of them. Each one needed coordinates recorded, brightness measured, and spectrum analyzed. Spectrum analysis reveals what an object is made of, how hot it is, and how fast it is moving through space. They compared Webb's observations with data from other telescopes. Hubble had looked at the same patches of sky years earlier, but could not see infrared light as well. Did the dots appear in Hubble's images at all? Some did, barely. Others were completely invisible to Hubble's less sensitive instruments. The Spitzer Space Telescope had also observed some of these regions before it was retired. Its infrared data, while less detailed than Webb's, provided additional clues. The team cross-referenced everything, building a complete picture of what these objects looked like across different wavelengths. Statistical analysis came next. When you observe hundreds of similar objects, patterns emerge. The team measured the distribution of brightness levels. They calculated the average size. They determined the typical spectrum. These statistical properties could be compared to theoretical models of different types of cosmic objects. Computer simulations ran constantly. The team modeled galaxies with different star formation histories. They simulated black holes with various masses and accretion rates. They tested scenarios involving dust, gas, and exotic matter. Each simulation generated predictions about what an object should look like. Those predictions were compared to the actual observations. Most simulations failed immediately. The parameters needed to match one property of the red dots would cause other properties to be completely wrong. A simulation that got the brightness right would predict the wrong color. One that matched the spectrum would fail to explain the size. The breakthrough came from thinking about the environment around black holes differently. Black holes do not sit naked in space. They attract material. Gas and dust spiral inward, forming an accretion disk. As this material falls toward the black hole, it heats up, it glows. It emits radiation. This radiation pushes against incoming material, creating a complex interaction of gravity and pressure. In mature black holes, This process is relatively clean. Material falls in steadily. The disk is well organized. Radiation escapes in predictable ways. But what about young black holes? Black holes in the process of rapid growth? Black holes surrounded by dense clouds of gas in the early universe? Watson's team modeled this scenario. A black hole wrapped in a cocoon of ionized gas. The gas so thick that light from the accretion disk had to pass through layer after layer of material before escaping into space. Each layer would absorb certain wavelengths and re-emit others. The overall effect would be like looking at a bright light through colored glass. The simulation matched the observations perfectly. The red color came from light filtering through dense gas. The brightness came from the intense energy of material falling into the black hole. The compact size made sense because even though the gas cocoon might extend for millions of kilometers, the brightest emission came from deep within, near the black hole itself. The temporal window fit too. Young black holes would be surrounded by abundant gas from the early universe. As they consumed that gas and grew larger, the cocoon would thin. Eventually, it would dissipate entirely, revealing a more typical active galactic nucleus. This evolution would take about 1 billion years, exactly matching when the red dots disappear from observations. Every piece of the puzzle clicked into place. The team wrote their findings carefully, knowing the implications were profound. They submitted the paper to Nature, one of the most prestigious scientific journals. Peer reviewers examined every claim, every calculation, every assumption. On January 14th, 2026, the paper was published. The mystery of the red dots was solved. A black hole is the end result of matter's collapse under its own gravity. When a massive star exhausts its fuel, it can no longer support itself against gravitational compression. The core implodes. If the star is large enough, the collapse continues past any stopping point. The core becomes infinitely dense, creating a region of space where gravity is so strong that nothing, not even light, can escape. That boundary, the point of no return, is called the event horizon. Cross it, and you are gone from the universe forever. Everything that falls past that line adds to the black hole's mass. The red dots contained black holes between 1 million and 10 million times the mass of our star, young by cosmic standards, small compared to the supermassive giants at the centers of mature galaxies, but still unimaginably massive by human measures. These black holes were not sitting dormant in empty space. They were actively feeding. Gas from the surrounding universe fell toward them. As the gas approached, gravity accelerated it to tremendous speeds. Particles collided with each other. Friction generated heat. Temperatures climbed into the millions of degrees. At those temperatures, atoms ripped apart into their constituent particles. Electrons separated from nuclei. The gas became plasma, a fourth state of matter beyond solid, liquid, and gas. This plasma emitted intense radiation across the electromagnetic spectrum: X-rays, ultraviolet light, visible light, infrared. The sheer amount of energy released was staggering. A black hole actively consuming matter can outshine an entire galaxy, but the red dots were surrounded by something unusual: a dense cocoon of ionized gas, left over from the primordial material that formed these early structures. This gas had not yet been blown away by radiation or consumed by the black hole. It wrapped around the entire system, creating a shroud layers thick. Radiation from near the event horizon had to fight through this cocoon to escape. High-energy X-rays and ultraviolet light were absorbed by the gas. The gas atoms captured this energy, then re-emitted it at longer wavelengths. This process repeated multiple times as light worked its way outward. By the time the radiation reached the outer edges of the cocoon and escaped into space, its character had changed. The original high-energy light from the accretion disk had been converted into infrared radiation. Specifically, the red portion of the infrared spectrum. Think of it like looking at a campfire through layers of smoke. The flames themselves burn blue-white at their hottest points, But through the smoke, the fire appears orange-red. The smoke absorbs the blue wavelengths and scatters the red ones, changing what you perceive. The cocoon served another purpose. It provided fuel for the black hole's growth. Material from the cocoon slowly spiraled inward, feeding the accretion disk, which fed the black hole. This created a cycle. The black hole consumed gas. The consumption generated radiation. The radiation heated more gas. Some of that heated gas fell inward to be consumed. The cycle continued, driving rapid growth. This feeding frenzy was temporary. Eventually, the radiation pressure would blow away most of the remaining cocoon. The black hole would consume what it could. The rest would be dispersed into space. The intense red glow would fade, replaced by the more familiar appearance of an active galactic nucleus. But during this growth phase, these black holes shone in a way we had never observed before. They represented a transient stage in black hole evolution, a messy adolescence between formation and maturity. That messiness is key to understanding why they appear the way they do. Numbers in astronomy get large quickly. Our planet weighs approximately 6 trillion kilograms, written out. That is a 6 followed by 24 zeros. It sounds massive. In cosmic terms, it is a speck of dust. Our star contains about 330,000 times Earth's mass. A decent-sized star, middle of the pack, nothing special. Across the galaxy, stars exist with masses 10 times greater. A few approach 200 times our star's mass before becoming unstable and tearing themselves apart. The red dots contain black holes between 1 million and 10 million times our star's mass. To put that in perspective relative to Earth, multiply our planet's mass by 330,000 to get our star's mass, then multiply that by 10 million. The result is a number so large it becomes meaningless in everyday terms. These black holes weigh more than 60 trillion kilograms. Writing that number would require 49 digits. But mass is only one measure of a black hole's size. The event horizon, the actual boundary of the black hole, depends on mass and nothing else. More mass means a larger event horizon. A black hole with 10 million times our star's mass has an event horizon roughly 30 million kilometers across. For comparison, Earth sits about 150 million kilometers from our star. The black hole's event horizon would fit inside our planet's orbit with room to spare, but it would still be enormous by any human standard. However, the event horizon is not what we observe. We cannot see the black hole itself. We see the material around it, the accretion disk, and the gas cocoon. That material can extend much farther. The accretion disk might stretch 10 million kilometers from the event horizon. Gas in the disk orbits at a significant fraction of light speed. The inner edge, closest to the black hole, completes an orbit in hours. The outer edge might take days or weeks. The gas cocoon surrounding the entire system could extend even farther, perhaps hundreds of millions of kilometers. This cocoon is not uniform. It has density variations, temperature gradients, and regions of different ionization states. Light passing through it gets absorbed, scattered, and re-emitted in complex ways. Despite their impressive mass, these black holes are actually small compared to what we typically observe in distant galaxies. Most active galactic nuclei contain black holes with masses of billions of times our star's mass, sometimes hundreds of billions. That is precisely why the red dots are important. They represent an earlier stage of growth. These are adolescent black holes, not yet grown to their final adult masses. They show us what supermassive black holes looked like when they were younger, hungrier, and wrapped in the dense gas of the early universe. Scientists had theorized that this phase must exist. Black holes do not appear fully formed at billions of solar masses. They must start smaller and grow over time. But until Webb's observations, we had never caught them in the act. The fact that these black holes are 100 times less massive than initially thought solves several problems. Smaller black holes are easier to form in the early universe. They require less time to accumulate their initial mass. They fit better within our models of how structure formation proceeded after the Big Bang. A 10 million solar mass black hole can form from the collapse of dense gas clouds in the first few 100 million years of cosmic history. A billion solar mass black hole cannot, not without invoking exotic processes we have never observed. These red dots show us black holes at a manageable size, growing through a violent but understandable process toward their eventual supermassive state. What happens during that growth process is even more remarkable. Black holes have a reputation for consuming everything around them. That reputation is only partially deserved. They do not suck in material like cosmic vacuum cleaners. They attract material through gravity, same as any massive object. If you replaced our star with a black hole of equal mass, Earth's orbit would not change. We would not spiral inward. We would just orbit in darkness. The real drama begins when material gets close. Gas falling toward a black hole does not fall straight in. It carries angular momentum, a measure of its rotation around the black hole. Conservation of angular momentum forces the gas into a disk shape, orbiting the black hole while slowly spiraling inward. As the gas spirals, particles rub against each other. Friction converts orbital energy into heat. The closer the gas gets to the black hole, the faster it orbits and the hotter it becomes. Near the event horizon, temperatures reach millions of degrees. At those temperatures, the gas emits intense radiation. This radiation pushes outward against the infalling material. For every kilogram of gas that crosses the event horizon, the energy released could power a small city for years. This makes actively feeding black holes among the brightest objects in the universe. Here is where the mess begins. Only a small fraction of the gas actually makes it to the event horizon. Most of the material in the accretion disk absorbs energy from radiation and friction. It heats up so much that it becomes buoyant, rising out of the disk plane. Some of it falls back down. Much of it gets ejected entirely, blown away into space by radiation pressure. The black hole also spins. As it rotates, it drags space itself around with it near the event horizon. This creates a region called the ergosphere, where matter cannot remain stationary. Material in the ergosphere gets caught in powerful magnetic fields anchored to the spinning black hole. These magnetic fields act like rails, channeling gas away from the disk's poles. The gas accelerates to incredible speeds, sometimes approaching light speed, and shoots out in narrow jets perpendicular to the accretion disk. These jets can extend for thousands of light years, carrying away enormous amounts of material and energy. Darrach Watson describes black holes as messy eaters for exactly this reason. They attract vast amounts of food, heat it to extreme temperatures, and then blow most of it back out through jets and radiation pressure. Perhaps 10% of the incoming gas actually crosses the event horizon. The rest gets recycled back into space. This inefficiency has profound consequences. A black hole surrounded by abundant gas will grow, but slowly. It must process vast amounts of material to increase its mass by even a small percentage. The process is violent, energetic, and wasteful. For the red dots, this messiness is visible in their spectra. The light coming from these objects shows signatures of material moving at high velocities. Some gas is falling inward at thousands of kilometers per second. Other gas is being ejected outward at similar speeds. The cocoon surrounding the black hole is being stirred by this turbulence. Material in the cocoon absorbs radiation from the inner accretion disk. It heats up and expands. Some of it falls back toward the black hole, getting recycled through the system. Some escapes into space, depleting the cocoon over time. The boundary between the cocoon and surrounding space is not sharp, but gradual, a transition zone where density drops and temperature falls. This chaotic feeding process is actually helping the black holes grow faster than they otherwise could. The dense cocoon provides a reservoir of material close to the black hole. Even though 90% gets blown away, the remaining 10% is still substantial because there is so much material to start with. In 1 billion years, the cocoon will be gone. The black hole will have grown. The feeding will become more organized and less obscured. These objects will look like typical active galactic nuclei, no longer glowing red. But for now, we are witnessing the messy childhood of supermassive black holes. Heat is just atoms moving. At room temperature, air molecules bounce around at about 500 meters per second. Your body temperature comes from atoms vibrating inside cells. Even ice contains molecular motion, just slowed down. As temperature increases, atoms move faster. Water boils at 100 degrees Celsius when molecules gain enough energy to break free from liquid and become vapor. Steel melts at around 1,500 degrees when atomic bonds can no longer hold the solid structure together. Near a black hole, temperatures transcend anything possible on Earth. Gas in the accretion disk heats through friction and compression. Inner regions, closest to the event horizon, reach temperatures of 10 million degrees Celsius. At these energies, atoms cannot exist as atoms. Electrons tear away from nuclei. Matter becomes plasma, a soup of charged particles. This plasma emits light differently than normal matter. Regular matter, like a hot piece of metal, glows because electrons jump between energy levels in atoms. The color depends on temperature. Red-hot metal is around 800 degrees. White-hot is over 1,200 degrees. Plasma does not follow those rules. Charged particles accelerate in magnetic fields and emit synchrotron radiation. Free electrons scatter off other particles and produce Bremsstrahlung radiation. The plasma glows across the entire electromagnetic spectrum simultaneously. X-rays dominate near the event horizon. These high-energy photons carry enormous amounts of energy, each one capable of ionizing thousands of atoms. They stream outward from the accretion disk in all directions. Most of these X-rays never escape the system. The gas cocoon surrounding the black hole intercepts them. When an X-ray photon hits a gas atom, several things can happen. The photon might ionize the atom, knocking an electron completely free. It might excite the atom, boosting an electron to a higher energy level. Or it might be absorbed entirely, its energy converted to heat. The heated gas re-emits this energy at longer wavelengths. Ultraviolet light, visible light, infrared. Each absorption and re-emission steps the energy down, like a waterfall with many small drops instead of one big one. By the time light escapes the outer layers of the cocoon, most of the original X-rays have been converted to infrared radiation. The cocoon acts as a giant filter, transforming high-energy light into lower-energy glow. Temperature gradients within the cocoon create different emission zones. The inner layers, close to the accretion disk, sit at hundreds of thousands of degrees. They emit primarily in ultraviolet. Middle layers, cooler but still searingly hot, emit visible and near-infrared light. Outer layers, at a mere few thousand degrees, emit far-infrared and radio waves. All these emission zones contribute to what Webb observes. The telescope's instruments collect infrared light from all the layers simultaneously. The combined signal produces the characteristic red color that gave these objects their nickname. Temperature also drives the cocoon's structure. Hot gas expands. It becomes less dense. Pressure tries to push it outward. Gravity tries to pull it inward. The balance between these forces determines the cocoon's size and shape. Near the accretion disk, radiation pressure dominates. Gas gets heated so intensely that it blows outward despite gravity's pull. This creates a wind, a flow of material away from the black hole. The wind carries mass and energy into the cocoon, stirring it up and preventing it from settling into a stable configuration. Farther out, gravity gains the upper hand. Cool gas in the outer cocoon slowly falls inward, feeding the accretion disk, which heats it and blows it back out. The cycle continues, maintaining the cocoon even as material is constantly exchanged between layers. This temperature-driven turbulence is part of why the black holes appear so messy. There is no calm, organized structure, just hot gas in constant motion, glowing intensely as it converts gravitational energy into light, and most of that light never even reaches the black hole. Imagine trying to drink from a fire hose. Water comes at you too fast, too much pressure. You might catch a few drops, but most of it sprays past, soaking everything around you. Black holes face the same problem when surrounded by abundant gas. The event horizon itself is small relative to the accretion disk. A 10 million solar mass black hole has an event horizon 30 million kilometers across. The accretion disk extends perhaps 10 times that distance. The gas cocoon stretches even farther. All that material is trying to funnel down into a relatively tiny opening. Physics prevents this from happening efficiently. As gas spirals inward through the accretion disk, it heats up. We covered the temperatures already, millions of degrees. At those temperatures, the gas emits intense radiation. This radiation does not just disappear into space. It pushes against the infalling gas, creating outward pressure. Think of radiation as a river of photons streaming away from the accretion disk. Each photon carries momentum. When photons hit gas atoms, they transfer that momentum, shoving the atoms backward. With enough photons pushing, the outward force can equal or exceed the inward pull of gravity. This balance point is called the Eddington limit. It defines the maximum rate at which a black hole can consume matter while remaining in equilibrium. Push beyond this limit, and radiation pressure becomes so strong that it blows away more gas than falls in. The black hole actually loses its food supply. The red dots appear to be feeding at or near their Eddington limit. They are consuming gas as fast as physics allows. But even at this maximum rate, 90% of the material gets ejected. Some gas gets blown away by radiation pressure in the disk itself. Photons push it outward until it escapes the system entirely. This material carries energy and angular momentum into space, never to return. Other gas gets channeled into jets. The black hole's rotation creates powerful magnetic fields near the event horizon. These fields act like particle accelerators, grabbing gas from the inner accretion disk and flinging it outward along the rotation axis at incredible speeds. The jets emerge perpendicular to the disk, shooting material in both directions like cosmic geysers. Gas in these jets can reach 10% of light speed. It carries enormous kinetic energy, enough to blow holes through the surrounding cocoon and impact material hundreds of thousands of light years away. Still more gas gets heated to such extreme temperatures that it simply expands away from the disk. Hot gas is buoyant. It rises above the disk plane, forming a corona of superheated plasma. Some of this plasma falls back down. Much of it escapes. The cocoon itself provides resistance. Dense gas surrounds the accretion disk on all sides. Material trying to fall inward must push through this cocoon, which slows it down and creates turbulence. The collision between infalling and outflowing gas generates shock waves, heating everything further and creating even more outward pressure. This is why Watson calls black holes messy eaters. The mechanism is inherently wasteful. For every kilogram of gas that crosses the event horizon and adds to the black hole's mass, 9 kilograms get blown back into space. But here is the key insight. Even 10% efficiency is enough when you start with massive amounts of material. The early universe was gas-rich. Dense clouds of primordial hydrogen and helium filled space. These young black holes sat in the middle of some of the densest regions. Gas surrounded them in abundance. Even wasting 90%, they still had plenty to feed on. A black hole consuming material at 10% efficiency can double its mass in roughly 10 million years. That might sound like a long time, but in cosmic terms, it is a blink. The universe had existed for 700 million years when these red dots appeared. 10 million years is less than 2% of that time span. Over the course of 1 billion years, a black hole could grow from 1 million solar masses to 100 million solar masses through this process. The math works. The physics allows it. We are watching it happen in real time, frozen in light from 13 billion years ago. The material that gets blown away does not vanish. It enriches the surrounding space. It heats neighboring gas clouds. It compresses matter in some regions and disperses it in others. This feedback affects how stars form in the vicinity and influences the growth of the host galaxy. In this way, the messiness serves a purpose. Black holes do not just grow themselves, they shape their environment, determining what happens in the space around them for millions of light years in all directions. Color in astronomy tells stories. Stars appear in different colors based on their surface temperature. Hot stars glow blue-white, with surface temperatures above 10,000 degrees. Cool stars glow red, below 3,000 degrees. Our star sits in the middle at about 5,500 degrees, appearing yellow-white. Galaxies show mixed colors. Young galaxies actively forming stars appear blue from all the hot, massive stars being born. Old galaxies with little new star formation appear red as their stellar populations age and cool. The color reveals the galaxy's history. The red dots were different. Too red, too uniform in their redness. Early theories suggested dust might be responsible. Dust grains in space absorb blue light more effectively than red light. When you look at a star through a dust cloud, it appears redder than it actually is. This effect, called reddening, is common in astronomy. But the amount of reddening needed to explain the red dots required absurd quantities of dust. Where would it all come from? Dust forms from elements heavier than hydrogen and helium. These elements get created inside stars and released when stars die. In the early universe, few stars had lived long enough to produce much dust. The spectrum provided the real clue. Webb does not just capture images, it splits light into its component wavelengths, creating detailed spectra that show exactly which colors are present and how bright each one is. The red dot spectra did not match stellar light. Stars produce a smooth, continuous spectrum called a blackbody curve, shaped by their temperature. The red dots showed emission lines, bright features at specific wavelengths corresponding to particular atoms emitting light. These emission lines indicated ionized gas, hydrogen stripped of its electron, oxygen, nitrogen, and other elements in highly ionized states. The gas was being heated by intense radiation from a central source, then cooling and emitting light at characteristic wavelengths. This pattern matched what astronomers see around active galactic nuclei, regions where supermassive black holes feed. But something was different. The emission lines appeared shifted and broadened in unusual ways. The overall spectrum peaked in the red and infrared, not in the blue or ultraviolet where you would expect from gas heated to millions of degrees. The answer came from modeling light transport through the gas cocoon. Start with the accretion disk near the black hole. It emits primarily X-rays and ultraviolet light, characteristic of plasma at 10 million degrees. These high-energy photons stream outward in all directions. When an X-ray hits a hydrogen atom in the dense cocoon, it ionizes the atom, knocking the electron completely free. The free electron carries kinetic energy, bouncing around and colliding with other atoms. These collisions heat the gas and create more ionizations. The energy from one X-ray photon gets distributed among many atoms. Eventually, electrons recombine with ions. When an electron falls back into orbit around a hydrogen nucleus, it emits a photon. The energy of this photon is lower than the original X-ray. It might be in the ultraviolet or visible range. This is called reprocessing. High energy input gets converted to lower energy output. The process repeats through multiple layers of the cocoon. Ultraviolet photons get absorbed and re-emitted as visible light. Visible light gets absorbed and re-emitted as infrared. Each step down in energy corresponds to moving redder in the spectrum. The cocoon's density matters enormously. Thicker cocoons cause more reprocessing. Light has to pass through more material, getting absorbed and re-emitted more times. By the time it escapes, it has been stepped down through multiple energy levels. The red dots have extremely dense cocoons. Their gas is thick enough that even after accounting for the expansion of space over 13 billion years, the original blue and ultraviolet light from the accretion disk has been almost completely converted to red and infrared. This is why they appear so distinctly red, not because the source is cool. The source is incredibly hot, but the filter between the source and our telescopes transforms the light, like looking at bright flames through thick, red glass. The cocoon also explains why the objects appear so compact. Most of the visible light comes from the inner regions of the cocoon, where density is highest and reprocessing is most efficient. The outer regions contribute less to the total brightness. This makes the objects look smaller than they actually are. Different wavelengths probe different depths into the cocoon. Longer infrared wavelengths can penetrate deeper before being absorbed. Shorter wavelengths get stopped in the outer layers. By observing at multiple wavelengths, astronomers can map the structure of the cocoon, determining its density profile and temperature gradient. The red color is a signature, a calling card. It tells us we are looking at young black holes surrounded by dense gas, caught in a specific evolutionary stage that lasts less than 1 billion years before the cocoon disperses. No other phenomenon in the universe produces quite this combination of brightness, color, and spectral features. That uniqueness is what finally allowed scientists to identify what the red dots truly are. Webb's deep field images cover tiny patches of sky. Imagine holding a grain of sand at arm's length. The area that grain covers is roughly how much sky Webb observes in a single deep field. From our perspective on Earth, it is almost nothing, a speck. Yet within that speck, hundreds of galaxies appear, and scattered among those galaxies are the red dots. The first deep field revealed about 50 red dots. Researchers thought they might be rare anomalies. Then Webb looked at another patch of sky. More red dots appeared in similar numbers. Another field, same result. A pattern emerged. These objects were not rare. They were common. Extrapolating from the observed density, astronomers estimate that hundreds of thousands of red dots existed across the entire observable universe during that era, perhaps millions. They represented a significant population of objects in the early cosmos, not oddities but a standard feature of galaxy formation at 700 million years after the Big Bang. This abundance solved one mystery while creating another. It explained why the objects appeared in every deep field Webb examined, but it raised the question of how so many black holes could form so quickly. Current models of black hole formation start with massive stars. A star at least 20 times our star's mass reaches the end of its life, exhausts its fuel, and collapses. The core implodes, creating a black hole with a mass between 5 and 100 times our star's mass. These stellar mass black holes can grow by accreting gas and merging with other black holes. Over hundreds of millions of years, they can reach masses of thousands or millions of solar masses. This process works well to explain black holes in the present-day universe. But the red dots appeared when the universe was only 700 million years old. There had not been time for many generations of stars to live and die. The first stars probably formed around 200 million years after the Big Bang. They lived for perhaps 1 to 10 million years before exploding. That leaves roughly 500 million years for black holes to grow from stellar mass remnants to the million to 10 million solar masses observed in the red dots. It is tight, but possible. A black hole consuming gas near the Eddington limit can double its mass every 10 million years. Starting from 100 solar masses, 50 doublings gets you to 10 million solar masses. The math works if conditions are right. The early universe provided those conditions. Dense gas clouds, minimal feedback from previous generations of stars, abundant fuel for rapid growth. The red dots show us black holes that took advantage of these favorable circumstances. Their abundance also tells us something about structure formation. For hundreds of thousands of these black holes to exist, hundreds of thousands of dense gas clouds must have collapsed and formed the seeds. This suggests that the early universe was more clumpy than some models predicted. Matter concentrated into dark matter halos faster than previously thought. Interestingly, not all galaxies from that era show red dots. Some early galaxies observed by Webb appear normal, forming stars without obvious signs of a central black hole. This indicates that black hole formation was common but not universal. Some gas clouds formed stars, others formed stars and black holes. The conditions determining which path a particular cloud took remain unclear. As more deep field images come in, the census of red dots grows. Each new observation refines our understanding of how many existed, how they were distributed across space, and how their properties varied. Some are brighter than others, some appear redder. These variations hint at differences in cocoon density, black hole mass, and accretion rate. Statistical studies of the population reveal correlations. Brighter red dots tend to be associated with denser regions of the early universe. This makes sense because denser regions provide more gas for the black hole to consume. The correlation between environment and black hole activity mirrors what we see in the present-day universe, where massive black holes preferentially reside in galaxy clusters. The discovery that these objects are common rather than rare fundamentally changes how we think about the early universe. We used to picture a simpler time, with small galaxies slowly assembling and black holes just beginning to form. Now we know it was far more dynamic. Black holes were everywhere, feeding voraciously, shaping their surroundings with intense radiation and powerful jets. The early universe was not a quiet nursery. It was a violent, energetic place where monsters were being born by the thousands. Development happens in stages. Children grow steadily for years, then hit growth spurts during adolescence. Stars form slowly from collapsing gas clouds, then ignite fusion in a sudden burst. Galaxies accumulate matter gradually, then undergo periods of intense star formation triggered by mergers. Black holes follow a similar pattern. They can grow slowly through trickle feeding over billions of years, or they can undergo rapid growth when conditions align, consuming vast amounts of material in relatively short periods. The red dots captured black holes during their growth spurt. This phase is characterized by several factors working together. First, abundant fuel. The black holes sit in regions with dense concentrations of primordial gas. Second, minimal feedback. In the early universe, previous generations of stars had not yet polluted their surroundings with heavy elements or blown away gas with supernovae. Third, efficient accretion. The gas is cold and dense, making it easier for gravity to pull it toward the black hole. During a growth spurt, a black hole can increase its mass by factors of 10 or more. A 1 million solar mass black hole can become a 10 million solar mass black hole in less than 100 million years. This acceleration explains how supermassive black holes reached billions of solar masses by the time the universe was 1 to 2 billion years old. The cocoon plays a crucial role in this rapid growth. It acts as a reservoir, holding gas close to the black hole where gravity can eventually pull it in. Without the cocoon, radiation pressure from the accretion disk would blow gas away before it could be consumed. The cocoon provides shielding, allowing material in its inner layers to slowly spiral inward despite the intense radiation. This creates a feedback loop. The black hole consumes gas, generating radiation that heats the cocoon. The heated cocoon expands slightly, but its density keeps most of the gas from escaping entirely. Some material falls back inward, feeding the black hole further. The cycle continues as long as the cocoon remains intact. Observations show that the black holes in red dots are accreting at rates close to their Eddington limit. This is the maximum rate physics allows for sustained growth. Exceeding this limit causes the radiation pressure to blow away the fuel supply faster than it can be replaced. The black holes are threading a needle, consuming gas as fast as possible without choking on their own luminosity. This high accretion rate cannot last forever. Eventually, the cocoon depletes. The black hole consumes the innermost gas. Radiation blows away the outer layers. Jets punch holes through the structure, allowing material to escape. The reservoir shrinks. As the cocoon thins, the red color fades. More high-energy light escapes directly without being reprocessed. The object begins to look like a typical active galactic nucleus, bright in ultraviolet and X-rays rather than red and infrared. The growth rate also slows. With less nearby gas to consume, the accretion rate drops. The black hole continues growing, but more gradually. It might take billions of years to add another factor of 10 to its mass. Timing matters here. The red dots appear during a specific window when the universe was between 500 million and 1.5 billion years old. Before that, conditions had not yet aligned to create the dense cocoons. After that, the cocoons had dispersed. This window represents a critical transition period in cosmic history. The first stars had formed and died, seeding space with heavier elements. Dense clumps of dark matter had pulled in gas, creating the environments where black holes could grow rapidly. But stellar feedback had not yet become strong enough to blow away all the fuel. We are witnessing a golden age of black hole growth, an era when conditions were perfect for rapid mass accumulation. Later, in cosmic history, star formation heated and dispersed gas, making it harder for black holes to feed efficiently. The early universe provided a brief opportunity, and the black holes took full advantage. This growth spurt phase fills a missing piece in our understanding of supermassive black hole evolution. We knew they had to grow from smaller seeds to their present-day masses. We knew the growth had to happen relatively quickly to produce billion solar mass giants by 1 billion years after the Big Bang. But we had never observed the process directly. Until now, the red dots show us black holes with their mouths full, growing as fast as physics allows. Every story has gaps. Archaeologists piece together ancient civilizations from fragments of pottery and ruins. They know what came before and what came after, but entire periods remain mysterious due to lack of evidence. Astronomy faces similar challenges when studying cosmic history. We can observe the present-day universe in exquisite detail. Galaxies, stars, planets, black holes, all accessible to our telescopes. We can also observe the very early universe through the cosmic microwave background, radiation from just 380,000 years after the Big Bang. But the period in between, from a few 100 million years to a few billion years after the Big Bang, has been difficult to study. This era, called the Cosmic Dawn and the Epoch of Reionization, saw the first stars ignite, the first galaxies assemble, and the first black holes form. We had theories about what happened. Models made predictions. Observational evidence was scarce. The Hubble Space Telescope pushed back the observational frontier, detecting galaxies at increasingly early times. But Hubble's instruments were optimized for visible and near ultraviolet light. The most distant objects emit their light in infrared wavelengths due to cosmic expansion stretching the light during its 13 billion year journey. Hubble could barely detect these objects, and studying them in detail was impossible. Webb changed everything. Its infrared capabilities allow detailed observations of the cosmic dawn. The red dots are a prime example. Hubble saw hints of these objects but could not resolve them. Webb revealed them clearly, enabling spectroscopic analysis and detailed study. The The discovery of red dots fills a specific gap in black hole evolution. We knew that supermassive black holes with billions of solar masses existed in galaxies just 1 billion years after the Big Bang. We knew that stellar mass black holes form from dying stars. But the connection between these two populations was unclear. How do you get from a 100 solar mass stellar remnant to a 1 billion solar mass supermassive black hole in less than a billion years? The math seemed impossible without invoking continuous feeding at maximum rates, or exotic formation mechanisms like direct collapse of massive gas clouds. The red dots demonstrate that standard feeding can work if conditions are right. A black hole starting at 1 million solar masses, feeding at the Eddington limit for several 100 million years, can reach tens of millions of solar masses. Multiple mergers between these black holes, combined with continued accretion, can produce the billion solar mass giants we observe at later times. This scenario requires a specific environment, dense gas to fuel rapid growth, minimal stellar feedback to avoid blowing away the fuel, enough time for multiple generations of growth and mergers. The early universe provided exactly these conditions. The red dots also reveal details about how galaxies and black holes co-evolve. Every massive galaxy contains a supermassive black hole at its center. The mass of the black hole correlates with properties of the galaxy, suggesting they influence each other's growth. This relationship must have been established early. The red dots show us black holes forming before their host galaxies have fully assembled. The intense radiation and jets from these young black holes affect the surrounding gas, heating it and preventing it from collapsing to form stars in some regions while triggering star formation in others. Understanding this feedback is crucial for explaining why galaxies have the properties they do. Without black hole feedback, gas would collapse too efficiently, forming stars at much higher rates than observed. Black holes regulate star formation, acting as thermostats that control how quickly galaxies grow. Before Webb, these ideas were theoretical. Models predicted strong black hole feedback in the early universe. The red dots provide direct observational evidence that this feedback was indeed occurring 700 million years after the Big Bang. The cocoons surrounding the black holes are part of this feedback system. Radiation from the accretion disk heats the cocoon. Jets inject energy into the surrounding medium. Material blown away from the black hole enriches nearby gas with energy and turbulence. All of this affects the larger environment, influencing what happens on scales of thousands or millions of light years. Filling this gap changes our overall picture of cosmic evolution. The early universe was not a simple place where matter slowly assembled into larger structures. It was dynamic, violent, and complex. Black holes grew rapidly. Galaxies formed in bursts. Feedback mechanisms shaped both. The red dots capture this complexity in action. What comes next in our understanding depends on continued observations. Webb will study more of these objects, building a comprehensive picture of their properties and evolution. Future telescopes, even more powerful, will push the frontier earlier still. But for now, we have turned on the lights in a previously dark chapter of cosmic history. 1 billion years after the Big Bang, astronomers found something that should not exist: quasars. Incredibly bright objects powered by black holes containing billions of solar masses. These monsters outshine entire galaxies, visible across nearly the entire observable universe. They represent the most extreme examples of black hole feeding, consuming material at prodigious rates. The problem was timing. 1 billion years sounds like a long time. In cosmic terms, it is barely the blink of an eye. For a black hole to reach 1 billion solar masses, it must start from something and grow. Stellar mass black holes, formed from dying stars, typically weigh between 5 and 100 times our star's mass. Going from 100 to 1 billion requires increasing the mass by a factor of 10 million. Even feeding continuously at the maximum possible rate, this growth takes time. The Eddington limit sets a speed limit on accretion. Push beyond it, and radiation pressure blows away your fuel faster than you can consume it. At the Eddington limit, a black hole can roughly double its mass every 10 million years. Starting from 100 solar masses, you need approximately 23 doublings to reach 1 billion. 23 doublings at 10 million years per doubling equals 230 million years of continuous feeding. Add the time needed for the first stars to form and die, roughly 200 million years, and you are already at 430 million years of the 1 billion available. This leaves little room for error. The black hole cannot take breaks. It cannot have periods of slow feeding. It must consume gas at maximum efficiency for nearly 500 million years straight. Some quasars appeared even earlier, at 800 million years after the Big Bang. These pushed the timeline to impossible extremes. There simply had not been enough time for stellar remnants to grow into billion solar mass giants through standard accretion. Theorists proposed exotic solutions, maybe supermassive black holes formed directly from the collapse of massive gas clouds, skipping the stellar remnant stage. Maybe they formed from dense clusters of stars collapsing together. Maybe primordial black holes, left over from the Big Bang itself, served as seeds. Each solution had problems. Direct collapse requires very specific conditions that might not occur often. Stellar cluster collapse faces similar challenges. Primordial black holes remain theoretical, with no observational evidence they exist. The red dots offer a simpler explanation. They show that standard accretion can work if it starts early and proceeds efficiently. If black holes began forming when the universe was just a few 100 million years old, they had more time to grow. A black hole forming at 200 million years, feeding steadily until 1 billion years, has 800 million years to accumulate mass. That is enough time for roughly 80 doublings, taking a 100 solar mass seed to well beyond a billion solar masses. The key is starting early and maintaining high accretion rates. The red dots demonstrate both. They show black holes actively feeding at 700 million years, already at masses of 1 to 10 million solar masses. These are not the billion solar mass giants yet, but they are well on their way. Multiple mechanisms can accelerate growth beyond simple gas accretion. Black holes can merge with each other. When two galaxies collide, their central black holes eventually spiral together and merge, combining their masses. A few strategic mergers can boost a black hole's mass significantly. The dense environment of the early universe made mergers more common. Galaxies were closer together. Interactions happened frequently. Black holes in the cores of merging galaxies had shorter paths to coalescence. Combining rapid accretion with occasional mergers provides a clear path from stellar mass seeds to supermassive giants within a billion years. No exotic physics needed. Just standard processes operating efficiently in a favorable environment. The red dots represent an intermediate stage in this evolution. They are past the initial stellar mass seed phase, but not yet evolved into the billion solar mass quasars. They bridge the gap, showing us black holes in the process of becoming supermassive. Observing them helps constrain models of black hole growth. We can measure their masses, their accretion rates, and their host galaxy properties. These measurements feed into simulations, allowing theorists to refine their predictions about how the first supermassive black holes formed. The timeline becomes less mysterious. What seemed impossible with too little time becomes plausible when you account for early formation and continuous feeding. The universe had barely begun, but already black holes were racing toward their adult masses. Every large galaxy contains a supermassive black hole. This is not speculation. It is an observed fact, confirmed by decades of measurements across thousands of galaxies. The Milky Way is no exception. At the exact center of our galaxy, 26,000 light-years from Earth, sits Sagittarius A star, a black hole with a mass of approximately 4 million times our star's mass. We cannot see Sagittarius A star directly. Black holes emit no light, but we can observe its effects on nearby objects. Stars orbit the galactic center in elliptical paths. Astronomers have tracked these stellar orbits for more than 2 decades, measuring positions and velocities with extreme precision. The orbits reveal the presence of an enormous mass concentrated in a tiny volume. Only a black hole fits the observations. One star, designated S2, completes an orbit every 16 years. At its closest approach, it comes within 17 light hours of Sagittarius A star, traveling at nearly 3% of light speed. The gravitational forces required to whip a star to such velocities can only come from a supermassive black hole. Our galaxy's central black hole is relatively quiet. It consumes very little material, producing minimal radiation. Occasionally, gas clouds or asteroids stray too close and get torn apart, creating brief flares of X-rays. But compared to the active galactic nuclei powering quasars and the red dots, Sagittarius A star is dormant. This was not always the case. Evidence suggests our galactic center was far more active in the past. X-ray telescopes have detected massive bubbles of hot gas extending 50,000 light-years above and below the galactic plane. These Fermi bubbles likely resulted from a powerful outburst from Sagittarius A star several million years ago. During that outburst, the black hole consumed large amounts of material, generating intense radiation and driving jets of energetic particles into the surrounding space. These jets inflated the bubbles, which remain visible today as faint X-ray and gamma-ray emissions. The quiet state of Sagittarius A star today tells us something important. Black holes do not feed continuously throughout cosmic history. They go through active phases when abundant fuel is available, then quiescent phases when fuel runs out. The red dots represent active phases. Our current galactic center represents a quiescent phase. This cycle has implications for galaxy evolution. During active phases, black hole feedback heats gas and prevents star formation in the galactic core. During quiescent phases, gas can cool and collapse, potentially triggering new bursts of star formation. The mass of Sagittarius A star, 4 million solar masses, is substantial but not extreme. Some galaxies host black holes with masses of tens of billions of solar masses. The mass correlates with properties of the host galaxy. Bigger galaxies tend to have bigger black holes. This correlation extends back to the early universe. The red dots exist in what will eventually become large galaxies. Their black holes, currently at 1 to 10 million solar masses, will grow over billions of years to match the correlation observed today. How did Sagittarius A star reach its current mass? We do not know the complete history. It likely started as a stellar mass black hole, or perhaps a small cluster of black holes that merged. Over billions of years, it accreted gas and merged with other black holes brought in by smaller galaxies colliding with the Milky Way. At some point, possibly during an era similar to what the red dots represent, Sagittarius A star went through a rapid growth phase. It fed voraciously on dense gas clouds, surrounded by a cocoon that allowed efficient accretion. Radiation from this phase might have appeared red and bright, similar to the objects Webb now observes in the distant universe. Then the fuel ran out. Star formation and supernova explosions heated gas in the galactic core, making it too hot to fall into the black hole. The accretion rate dropped. Sagittarius A star entered its current quiet state, interrupted only by occasional snacks when stars or gas clouds wander too close. This life cycle, from rapid growth to quiescence, appears to be standard for supermassive black holes. The red dots show us the growth phase. Sagittarius A star shows us the quiet aftermath. Together, they tell the complete story of how black holes evolve from small seeds to massive giants to dormant monsters lurking at the hearts of galaxies. Understanding our own galactic center provides context for interpreting distant observations. When we study the red dots, we are looking at objects that may one day resemble Sagittarius A star. When we study Sagittarius A star, we are seeing the endpoint of processes that began when objects like the red dots were feeding billions of years ago. The connection spans cosmic time, linking the violent youth of the universe to the relatively calm middle age we inhabit now. Picture a cocoon surrounding a growing black hole. Not a solid structure. Gas does not form rigid shells in space. Instead, think of layers of varying density, like an onion. The innermost layer sits closest to the accretion disk. It experiences the most intense heating and radiation. The outermost layer borders the surrounding intergalactic medium, gradually fading into empty space. Each layer serves a function in the fuel delivery system. The outer layers act as a reservoir. They contain vast amounts of gas, millions of solar masses of hydrogen and helium, left over from the Big Bang. This gas is relatively cool, just a few thousand degrees. Cool enough that gravity can hold it together despite its thermal pressure trying to push it apart. Gravity from the black hole and the surrounding dark matter halo pulls this gas inward, but it does not fall straight in. Conservation of angular momentum forces it into spiral patterns. Some gas gains energy through collisions and escapes. Most continues inward, slowly working its way toward the center. As gas moves to deeper layers, density increases. More matter occupies less space. Particles collide more frequently. These collisions transfer energy, heating the gas. Temperature rises from thousands to tens of thousands of degrees. At these temperatures, hydrogen begins to ionize. Electrons separate from protons. The gas becomes electrically conductive. Magnetic fields embedded in the gas start to matter. They can channel flows, create instabilities, and link different regions of the cocoon together. Middle layers of the cocoon absorb radiation from the accretion disk. X-rays and ultraviolet photons streaming outward ionize atoms and heat gas. This absorbed energy gets re-emitted at longer wavelengths. The middle layers glow in visible and near-infrared light. These layers also provide shielding for the inner layers. Without the middle layers absorbing high-energy radiation, the inner layers would be heated to such high temperatures that gas could not remain bound. The middle layers act as insulation, protecting the inner fuel supply from the black hole's own luminosity. The innermost layers sit on the boundary between the cocoon and the accretion disk. Here, density reaches extreme values. Gas is compressed by both gravity and the pressure of overlying layers. Temperatures climb to hundreds of thousands of degrees. This is the critical transition zone. Gas in this region must make a choice, determined by whether it has enough angular momentum to orbit or whether it will fall directly inward. Most has too much angular momentum. It joins the accretion disk, spiraling inward while slowly losing energy to friction. The accretion disk itself is not part of the cocoon. It is a separate structure, a flattened, rotating disk where gas reaches millions of degrees and emits the intense radiation we observe. But the boundary between disk and cocoon is not sharp. Material flows back and forth. Gas blown out of the disk by radiation pressure re-enters the cocoon. Gas from the cocoon settles into the disk. This flow pattern creates a circulation system. Like a fountain, material rises and falls, driven by heating and cooling. Hot gas expands outward. It cools as it expands and radiates away energy. Cooler gas becomes denser and falls back inward. The cycle continues, churning the cocoon and preventing it from settling into a stable equilibrium. The cocoon's density structure determines how efficiently the black hole can feed. Too diffuse, and gravity cannot pull gas inward effectively. Radiation pressure blows it away before it reaches the accretion disk. Too dense, and the opacity becomes so high that radiation cannot escape. The system chokes on its own luminosity. The red dots sit in a sweet spot. Their cocoons are dense enough to shield the inner regions and maintain high infall rates. Dense enough to reprocess radiation efficiently, creating the red color, but not so dense that they become completely opaque or thermally unstable. This balance is temporary. As the black hole consumes gas, the cocoon depletes. The density drops. Shielding becomes less effective. More high-energy radiation escapes. The infall rate decreases. Over hundreds of millions of years, the cocoon gradually disperses. Jets also disrupt the cocoon. Powerful outflows from the black hole's poles punch holes through the gas layers. Material escapes through these channels. Energy and momentum carried by the jets stir up the cocoon, creating turbulence and driving additional mass loss. Eventually, the cocoon is gone. The black hole sits in a more typical environment, surrounded by lower density gas. Feeding continues, but at reduced rates. The rapid growth phase ends. The red color fades. What remains looks like a normal active galactic nucleus. But during its brief existence, the cocoon enabled growth rates that would be impossible otherwise. It transformed a modest black hole into a massive one in a fraction of a billion years. The red dots do not last. Webb observes them at redshifts corresponding to 700 million years after the Big Bang. Similar observations at later cosmic times, around 1.5 billion years after the Big Bang, show far fewer of these objects. By 2 billion years, they have essentially disappeared. This vanishing act tells us the red dot phase is transient. Several factors contribute to their disappearance. First, the cocoons disperse. As black holes consume gas and jets blow material away, the dense shrouds surrounding them thin out. Without the cocoon to reprocess radiation, the red color fades. The objects no longer appear as distinctive red dots. They do not actually disappear. They transform. The same black holes that powered the red dots still exist. But they look different. Their spectra change. Their colors shift. They start resembling typical active galactic nuclei, bright in ultraviolet and X-rays rather than red and infrared. Second, the fuel supply diminishes. The early universe had abundant primordial gas. This gas had not yet been processed through stars or heated by previous generations of black hole activity. It was cold, dense, and easy for gravity to pull into black hole accretion disks. As the universe aged, conditions changed. Star formation heated gas. Supernovae explosions dispersed it. Black hole feedback, including radiation from objects like the red dots, ionized and energized surrounding material. All these processes made it harder for gas to collapse and feed black holes. By 2 billion years after the Big Bang, much of the easily accessible gas had been consumed or dispersed. Black holes still fed, but more slowly. Accretion rates dropped from near the Eddington limit to a fraction of that maximum. Lower accretion rates meant less luminosity and weaker observable signatures. Third, the black holes themselves evolved. A black hole with 10 million solar masses feeding at high rates for a few 100 million years becomes a black hole with hundreds of millions of solar masses. More massive black holes have larger event horizons and different accretion disk properties. The relationship between black hole mass and luminosity is not linear. Bigger black holes can be brighter in absolute terms, but they are also farther from their Eddington limit if feeding on the same amount of gas. The efficiency of converting accreted mass to radiation changes with black hole mass and accretion rate. These combined effects mean that the specific conditions producing red dots existed for a limited time window. Before 700 million years, the universe was still setting up. Stars were just beginning to form. Black holes were small or non-existent. Dense gas cocoons had not yet assembled around them. Between 700 million and 1.5 billion years, conditions aligned perfectly. Black holes had grown to intermediate masses. Dense gas remained abundant. Cocoons formed and persisted. Rapid feeding occurred. Red dots appeared across the sky. After 1.5 billion years, the window closed. Cocoons dispersed. Fuel became scarce. Black holes transitioned to slower growth modes. The red dot phase ended, replaced by other types of active galactic nuclei that look different when observed. This life cycle parallels what we see in stellar evolution. Stars spend most of their lives in stable phases, fusing hydrogen in their cores, but they also pass through brief transitional phases, like the red giant stage, that last only a small fraction of their total lifetime. These transitional phases are rare to observe at any given moment, but common over cosmic history because every star passes through them. The red dots represent a transitional phase for black holes. Not all black holes go through it, not all that do spend the same amount of time in it, but it is common enough that hundreds of thousands existed simultaneously during the relevant epoch. By studying how many red dots exist and how their numbers change over time, astronomers can constrain models of black hole growth and galaxy evolution. The appearance and disappearance timescales provide clues about gas depletion rates, cocoon lifetimes, and the efficiency of feedback processes. The fact that we see red dots at 700 million years but not at 2 billion years tells us something fundamental about how the universe was changing during that interval. The cosmic dawn was ending. The universe was transitioning from a gas-rich, star-forming youth to a more mature state where structure had already assembled. Catching this transition in action is valuable. It is one thing to theorize about how cosmic evolution proceeds. It is another to observe it directly, watching objects appear, transform, and fade as the universe ages around them. When the red dots were first discovered, one assumption seemed obvious. Objects this bright must be massive. To shine across 13 billion light-years and still be detectable, they must contain enormous amounts of matter, generating vast quantities of energy. Early estimates suggested black holes with hundreds of millions or even billions of solar masses. Those estimates were wrong. Off by a factor of 100. The actual black holes in red dots weigh between 1 million and 10 million solar masses, still massive by everyday standards, still capable of tremendous gravitational effects, but far smaller than initially thought. This realization was crucial to solving the puzzle. Smaller black holes are easier to explain in the early universe. Forming a billion solar mass black hole 700 million years after the Big Bang requires either exotic physics or impossibly efficient accretion. Forming a 10 million solar mass black hole is challenging but achievable through standard processes. Start with a stellar mass seed, feed it steadily, wait a few 100 million years, you get there. The brightness of the red dots comes not from their black hole mass, but from their accretion rate. They are feeding at or near the Eddington limit, the maximum rate physics allows. At this rate, even a modest mass black hole can produce enormous luminosity. Think of it like a small engine revving at maximum RPM versus a large engine idling. The small engine, pushed to its limits, can produce as much power as a much larger engine running at a fraction of capacity. The red dots are small black holes running at full throttle. This also explains why they are so messy. High accretion rates mean more material trying to funnel into the black hole than can fit through the event horizon efficiently. The excess gets blown away, creating powerful winds and jets. The dense cocoon helps channel some of this excess back toward the disk, but even so, most material gets ejected. The growth rate follows naturally from the physics. A 10 million solar mass black hole at the Eddington limit can double its mass in roughly 10 million years. Starting from 1 million solar masses, 7 doublings over 70 million years reaches 128 million solar masses. 300 million years of feeding could produce black holes approaching 1 billion solar masses. These growth rates are faster than what we observe in present-day galaxies, where black holes grow much more slowly. But the early universe provided better conditions. More gas, less stellar feedback, fewer processes disrupting accretion. Black holes could maintain high feeding rates for longer periods. The small size also helps explain the cocoon structure. A smaller black hole has a smaller sphere of influence, the region where its gravity dominates. Gas outside this sphere orbits or flows in response to other gravitational sources. gas inside falls toward the black hole unless supported by pressure. A 10 million solar mass black hole has a sphere of influence extending a few light years. The cocoon wraps around this region, concentrated where the black hole's gravity is strongest. This compact configuration makes sense given the limited volume involved. Larger black holes would have correspondingly larger spheres of influence and more extended cocoons. The cocoon material would be spread over greater distances, reducing its density. Lower density means less efficient reprocessing of radiation and a different observational signature. The compact, dense cocoons of the red dots fit best with modest mass black holes. Interestingly, being smaller makes these black holes more common. Forming millions of 10 million solar mass black holes across the universe is much easier than forming millions of billion solar mass ones. The abundance of red dots makes sense in this context. They represent a standard stage in black hole evolution, not a rare, exotic phenomenon. The combination of small mass and high accretion rate also impacts the black hole's environment. Feedback from a 10 million solar mass black hole feeding at maximum rate is intense but localized. It affects the immediate surroundings strongly, but has limited reach beyond a few thousand light-years. This localized feedback contrasts with the galaxy-scale effects produced by billion solar mass black holes in quasars. Those monsters regulate star formation across their entire host galaxy. The red dots influence smaller regions, allowing star formation to continue in outer parts of the proto-galaxy even while the central region is dominated by black hole activity. Understanding that the black holes are smaller than expected changes our interpretation of their role in cosmic evolution. They are not anomalies requiring new physics. They are standard objects caught during a brief, intense growth phase, smaller, faster, messier than their mature descendants. But following the same fundamental rules, science loves elegance. When observations do not match expectations, the temptation is to invent new explanations, new particles, new forces, new rules that apply only under exotic conditions. Sometimes this is necessary. Dark matter and dark energy required new physics because no conventional explanation fit the data. But often, the simplest answer is the right one. The red dots prove this principle. When astronomers first saw objects that bright appearing so early in cosmic history, panic set in among theorists. Models of galaxy formation could not produce such massive structures in the available time. Something had to be wrong. Either our understanding of gravity was incomplete, or star formation worked differently in the early universe, or black holes formed through processes we had never observed. Papers proposed direct collapse scenarios where massive gas clouds imploded to form black holes without passing through a stellar phase. Others suggested primordial black holes from the Big Bang itself served as seeds. Some even questioned whether our measurements of cosmic time were correct, wondering if the universe might be older than calculated. All these exotic explanations shared a common feature. They required adding new elements to our physics toolkit, new mechanisms, new initial conditions, new assumptions about how matter behaves under extreme circumstances. The red dot solution requires none of this. Start with a massive star. It forms, lives, and dies within a few million years. The core collapses into a stellar mass black hole, perhaps 50 or 100 times our star's mass. This is standard astrophysics, observed countless times in the present-day universe. The black hole sits in a dense region of the early universe, surrounded by abundant gas. Gravity pulls this gas inward. It forms an accretion disk. The disk heats up through friction. Radiation streams outward. Some gas falls into the black hole. Most gets blown away. Again, standard physics. We observe this in active galactic nuclei throughout cosmic history. The key difference in the early universe is environmental. More gas available, less stellar feedback to heat and disperse it. These are changes in conditions, not changes in physical laws. The processes work the same way. The efficiency and timescales differ because the ingredients differ. Feed a black hole steadily for a few 100 million years. It grows. 10 doublings of mass, each taking 10 to 20 million years. 100 solar masses becomes 100,000, then 10 million. Then approaching a billion. The math works. The timeline fits. No exotic physics required. The dense cocoon surrounding these growing black holes follows naturally from the gas-rich environment. Dense gas absorbs and reprocesses radiation. This creates the red color. The cocoon structure arises from standard radiative transfer through ionized gas. Every step can be calculated using well-understood equations. Even the disappearance of red dots after a billion years requires no new physics. Gas gets consumed. Stellar feedback heats remaining gas. Cocoons disperse. Black holes continue growing but more slowly. The transition from red dot to typical active galactic nucleus follows from straightforward evolution of the gas supply. This simplicity is powerful. It means our fundamental understanding of how black holes work is correct. The same processes operating in nearby galaxies today operated 13 billion years ago. Physical laws do not change with cosmic time. Only conditions change. Watson's team emphasized this point in their Nature paper. The observations fit existing theoretical frameworks. The surprise was not that black holes could grow this way, but that we had finally caught them in the act. Previous observations lacked the sensitivity to detect these objects. Webb provided the missing observational capability. This has broader implications for cosmology. If black hole growth in the early universe required exotic physics, it would suggest our models of structure formation were fundamentally flawed. We would need to rethink how galaxies assembled, how dark matter clumped, how feedback processes operated. Instead, the red dots validate those models. They show that standard processes, operating under early universe conditions, produce the results we observe. This gives confidence that our overall picture of cosmic evolution is on the right track. There are still mysteries. We do not fully understand every detail of how gas flows in accretion disks. Magnetic fields play roles we are still working out. Turbulence creates complexities that challenge our simulations. But these are engineering problems, not fundamental physics problems. We know the basic rules. We are refining our understanding of how they apply in specific situations. The elegance of the red dot explanation lies in its mundanity. These are not exotic objects requiring revolutionary new ideas. They are familiar objects, black holes and gas, doing familiar things, accreting and radiating. We simply had never observed them at this particular stage of their life cycle before. Sometimes the universe surprises us by being straightforward. The red dots are one of those times. A black hole is small. The light it generates is enormous. This paradox confuses people. How can something with an event horizon a few million kilometers across outshine objects hundreds of thousands of light years in size? The answer lies in understanding what we actually observe. The event horizon is a boundary, not a physical surface. It marks the point where escape velocity equals light speed. Cross that boundary moving inward, and you can never leave. Not because of any barrier, but because space-time itself curves so sharply that all paths lead inward. For a 10 million solar mass black hole, the event horizon radius is roughly 15 million kilometers. That is about 1/10 the distance from Earth to our star. Small on cosmic scales, the entire black hole proper would fit comfortably inside our planet's orbit. We cannot see the event horizon. No light escapes from inside it by definition. What we observe is the material around the black hole, primarily the accretion disk and the gas cocoon. The accretion disk extends much farther than the event horizon. Gas orbits at various distances, from just outside the event horizon to perhaps 10 times that radius. The entire disk might span 150 million kilometers, roughly the size of Earth's orbit around our star. But even the disk is not what makes these objects so bright. The luminosity comes from energy conversion. As gas spirals inward through the disk, it loses gravitational potential energy. This energy does not disappear. It converts to heat and radiation. The efficiency of this conversion is remarkable. For every kilogram of gas that crosses the event horizon, roughly 10% of its rest mass energy gets converted to light. Compare that to nuclear fusion, the process powering stars. Fusion converts less than 1% of rest mass to energy. Black hole accretion is 10 times more efficient. It is the most efficient energy generation mechanism in the universe besides matter-antimatter annihilation. A black hole feeding at the Eddington limit, consuming the maximum amount of gas that physics allows, generates luminosity proportional to its mass. More massive black holes can sustain higher absolute accretion rates and produce more total light, but the relationship is linear: double the mass, double the maximum luminosity. However, a smaller black hole feeding at its Eddington limit has a higher luminosity per unit mass. It shines more efficiently relative to its size. This is counterintuitive, but follows from the physics of radiation pressure and gravity. The red dots demonstrate this principle. Their black holes, at 10 million solar masses, are relatively small, but feeding at near Eddington rates, they produce luminosities equivalent to billions of times our star's brightness. This makes them visible across 13 billion light-years despite their modest mass. The cocoon amplifies the observational signature. While the accretion disk generates the original energy, the cocoon spreads that energy over a larger volume and reprocesses it to wavelengths where Webb is most sensitive. This makes the objects easier to detect than they would be if we only saw the bare accretion disk. Think of it like a light bulb and a lampshade. The bulb is small and produces the light. The lampshade is much larger and determines how that light appears to an observer. The lampshade does not generate energy, but it shapes what we see. The cocoon acts as a lampshade for the black hole. It takes concentrated high-energy radiation from a small volume and redistributes it as lower-energy radiation from a larger volume. This changes the object's observational properties without changing the fundamental energy source. Brightness also depends on distance and cosmic expansion. The farther away an object sits, the dimmer it appears. Light spreading out over larger areas becomes more diffuse. For the red dots, light has traveled 13 billion years, spreading across a sphere whose surface area has increased by factors of billions. Additionally, cosmic expansion stretches light to longer wavelengths. This redshift reduces the energy of individual photons. The combined effect of spreading and redshifting means we receive only a tiny fraction of the light originally emitted. Yet the objects remain detectable because the original luminosity was so high. Understanding this distinction between physical size and brightness is crucial for interpreting observations. A small object can be bright, a large object can be dim. Size and luminosity are related but not the same thing. The red dots are compact sources of immense energy. Their physical extent, measured by the event horizon or even the accretion disk, is modest. Their energy output rivals entire galaxies. The mismatch between size and brightness is what makes them special and what initially made them so puzzling. Now that we understand the mechanism, the brightness makes sense. Small black holes fed enormous amounts of gas, converting mass to energy at maximum efficiency, wrapped in cocoons that optimize detection at infrared wavelengths. Every piece contributes to making these objects visible across the observable universe. Black holes spin. When matter collapses to form a black hole, it conserves angular momentum. If the original star or gas cloud was rotating, the resulting black hole rotates too. This spin has profound effects on the surrounding environment. A spinning black hole drags space-time around with it. Close to the event horizon, this frame dragging becomes so strong that nothing can remain stationary relative to distant space. Everything gets pulled along with the rotation, like leaves caught in a whirlpool. This dragging creates the ergosphere, a region outside the event horizon where space-time itself rotates. Material in the ergosphere must move, forced by geometry rather than by force. The faster the black hole spins, the larger the ergosphere extends. Magnetic fields thread through the accretion disk and the ergosphere. These fields anchor to the ionized gas in the disk. As the disk rotates, it twists the magnetic field lines. The twisting continues until tension in the field becomes enormous. Eventually, the fields release their energy. They snap into configurations that channel matter along the rotation axis of the black hole. This creates jets, narrow beams of gas and energy shooting outward from the poles at tremendous speeds. Jets can reach velocities approaching light speed. Material accelerates through electromagnetic forces, gaining kinetic energy far beyond what gravity alone could provide. The particles in jets glow intensely, emitting radiation across the electromagnetic spectrum. For the red dots, jets play a crucial role in shaping the cocoon and regulating growth. As jets punch through the dense gas surrounding the black hole, they create cavities. Imagine a drill boring through soft material. The jets clear paths through the cocoon, allowing radiation and matter to escape more easily along the polar directions. This anisotropic escape pattern affects how we observe the objects. If we view a red dot from an angle near the jet axis, we see different properties than if we view it edge-on through the equatorial cocoon. The viewing angle introduces scatter in the observed properties of these objects. Jets also carry away energy and mass that would otherwise fall into the black hole. Estimates suggest that jets can remove up to 50% of the energy generated in the accretion disk. This energy extraction limits how fast the black hole can grow, providing a feedback mechanism that regulates the system. The rotation rate of the black hole matters. Faster spinning black holes generate more powerful jets. They also have larger ergospheres and more efficient energy extraction from the accretion disk. Slower spinning black holes produce weaker jets or none at all. We cannot directly measure the spin of black holes in the red dots. The observations lack sufficient resolution and signal to noise, but theoretical models suggest they likely spin rapidly. Black holes grow by accreting gas from a preferred direction, the plane of the accretion disk. This adds angular momentum efficiently, spinning up the black hole over time. A rapidly spinning black hole can have a rotation speed approaching the maximum allowed by physics, where the event horizon surface moves at nearly light speed. At these extreme spins, the ergosphere extends far from the event horizon and jet power reaches its peak. The jets from red dots probably extend for thousands of light years beyond the cocoon. They impact the surrounding intergalactic medium, creating shock waves and heating gas. This feedback affects star formation in nearby regions and shapes the evolution of the host protogalaxy. In the present-day universe, jets from active galactic nuclei can extend for millions of light years. They create enormous radio-emitting lobes visible to telescopes sensitive to long wavelengths. The jets from red dots, though likely smaller due to the younger age and smaller black hole mass, follow the same basic physics. Rotation couples the black hole to its environment in fundamental ways. Without rotation, black holes would be simpler objects, spherically symmetric and predictable. With rotation, they become engines capable of launching jets, extracting energy from their own spin and influencing their surroundings far beyond the event horizon. The messy eating habits of black holes become even messier when rotation and jets enter the picture. Material does not just fall in and get blown away. It gets accelerated to relativistic speeds, collimated into narrow beams, and shot across thousands of light years of space. This complexity is part of what makes black holes such important players in cosmic evolution. They are not passive objects simply responding to their environment. They actively shape it through radiation, winds, and jets. Every journey has stages. The red dots represent one stage in a black hole's life, not the beginning, not the end. A middle phase characterized by rapid growth and distinctive observational properties. Understanding where they came from and where they are going completes the picture. Before the red dot phase, the black hole was smaller, perhaps a stellar mass object formed from a collapsing star, perhaps a seed black hole created through direct collapse of a dense gas cloud. Either way, it weighed less than 1 million solar masses. This early black hole sat in a forming galaxy, surrounded by gas but not yet feeding efficiently. The gas had not settled into an organized accretion disk. The environment was chaotic. Star formation proceeded in bursts. Supernovae explosions stirred up the gas, sometimes feeding the black hole, sometimes pushing gas away. Over tens of millions of years, the system organized. Gas lost angular momentum through collisions and friction. It fell toward the center, forming a disk. Density increased. The accretion rate rose. The black hole began its growth spurt. The cocoon formed as gas accumulated around the central region. Radiation from the nascent accretion disk ionized this gas. It heated and expanded, but remained bound by gravity. The density reached the point where reprocessing became efficient. The object entered the red dot phase. For several 100 million years, the black hole fed voraciously. It consumed gas at near maximum rates. Its mass increased by factors of 10 or more. The cocoon persisted, maintained by continuous infall of gas from the surrounding proto-galaxy. Then conditions changed. Star formation in the host galaxy accelerated. Massive stars formed, lived briefly, and exploded as supernovae. These explosions heated gas in the galaxy. They also produced heavy elements, polluting the primordial hydrogen and helium with metals. Heated, metal-enriched gas is harder to accrete. It has higher pressure, resisting gravitational collapse. It cools less efficiently, remaining buoyant longer. The infall rate onto the black hole decreased. Simultaneously, the black hole's own feedback intensified. As it grew more massive, its gravitational influence extended farther. Its jets became more powerful. Radiation pressure affected a larger volume. These feedback processes pushed gas away from the central region. The cocoon began to thin. Outer layers dispersed into the intergalactic medium. Inner layers were consumed by the black hole or blown away by jets. The density dropped below the threshold for efficient reprocessing. As the cocoon dissipated, the object's appearance changed. The red color faded. More high-energy radiation escaped directly without being converted to infrared. The object started to resemble a typical active galactic nucleus, bright in ultraviolet and X-rays. The black hole continued growing, but more slowly. Without the dense cocoon providing a reservoir of nearby fuel, it had to rely on sporadic infall from larger distances. The accretion rate dropped well below the Eddington limit. Growth proceeded over billions of years rather than hundreds of millions. The host galaxy evolved simultaneously. Stars formed from gas not consumed by the black hole. Smaller galaxies merged with the host, bringing additional stars, gas, and sometimes their own black holes. Each merger could trigger new bursts of accretion and star formation. By the time the universe reached a few billion years old, the red dots had transformed into quasars and active galactic nuclei. The black holes now weighed hundreds of millions to billions of solar masses. They powered some of the brightest objects in the universe, visible across cosmic distances. Later still, as gas supplies dwindled and star formation slowed, the black holes entered quiescent phases. They still existed at galactic centers, still massive, but no longer actively feeding. Like Sagittarius A star in our own galaxy, they became dormant, waiting for the next gas cloud or star to wander too close. This life cycle, from stellar remnant to red dot to active nucleus to quiescent giant, spans billions of years. Each phase has characteristic properties. Each phase plays a role in shaping the host galaxy. The red dot phase, though brief, is critical. It represents the period of most rapid growth. It establishes the black hole's mass and sets the stage for later evolution. Without the intense feeding during this phase, black holes could not reach the billions of solar masses we observe in mature galaxies. Tracing this evolution helps us understand not just black holes but galaxies themselves. The two are intimately connected. Black hole growth affects star formation. Star formation affects gas supply for black holes. Mergers impact both. The coevolution of black holes and galaxies is one of the central themes of modern astrophysics. The red dots show us this coevolution at an early stage, when the rules were still being established and the structures we see today were just beginning to form. Science is not just about cataloguing objects in space. It is about understanding how the universe works. Every new discovery either confirms our theories or forces us to revise them. The red dots do both. They confirm that black holes can grow from stellar mass seeds to supermassive giants through standard accretion processes. No exotic physics needed, no new fundamental forces, just gravity, gas, and time. This validation is important. It means our models of black hole growth are fundamentally sound, but they also revise our timeline. Before Webb, we thought rapid black hole growth occurred primarily during galaxy mergers, violent events where two galaxies collide and their gas supplies compress. The red dots show that rapid growth happened earlier, before major mergers, when galaxies were just forming. This earlier growth phase has consequences for everything that came after. Black holes influence their host galaxies through feedback, radiation, and jets heat gas, preventing it from cooling and forming stars. This regulation is why galaxies do not convert all their gas into stars immediately. Black hole feedback creates the diversity of galaxy types we observe. If black holes reached significant masses earlier than previously thought, their feedback started earlier too. This affects the first billion years of cosmic history more than models accounted for. Star formation rates, galaxy sizes, and the abundance of different galaxy types all depend on when black hole feedback becomes important. The red dots also inform our understanding of structure formation. The fact that hundreds of thousands of these objects existed means that dark matter halos capable of hosting them were common. Dense regions where gas could accumulate and feed black holes efficiently dotted the early universe. This clumpiness in dark matter distribution affects how galaxies form and where they appear. It influences the large-scale structure of the cosmos, the web of filaments and voids that characterizes the distribution of matter on the largest scales. Additionally, the red dots provide a new tool for studying the early universe. Their distinctive spectral signatures make them excellent targets for detailed follow-up observations. By studying many of them across different cosmic times and environments, astronomers can map how conditions changed as the universe evolved. Each red dot is like a probe, sampling the gas density, temperature, and composition at a specific location and time. Collectively, they paint a picture of the early universe in unprecedented detail. The discoveries also have philosophical implications. We often think of cosmic history as progressing from simple to complex. The Big Bang was pure energy. It cooled and formed particles. Particles formed atoms. Atoms formed stars. Stars formed galaxies. Complexity emerging from simplicity. The red dots remind us that even early in this progression, the universe was already complex. Black holes feeding in dense cocoons, jets shooting across thousands of light years, feedback mechanisms regulating star formation. All this happened when the universe was barely 5% of its current age. Complexity does not require billions of years to develop. Given the right conditions, it emerges rapidly. The early universe was not a simple place. It was dynamic, violent, and full of processes we are still working to understand. This realization humbles us. We have sophisticated theories and powerful telescopes. We can detect objects across 13 billion light-years and analyze their properties in detail. Yet, surprises still await. Objects like the red dots existed for decades in images before we understood what they were. How many other phenomena are hiding in plain sight, waiting for the right combination of technology and insight to reveal them? What will the next generation of telescopes discover when they push even farther back in time, closer to the Big Bang itself? The red dots also demonstrate the value of observation-driven science. Theory can predict what might exist, but without observations to test those predictions, we are speculating. Webb provided the observations, scientists interpreted them, understanding advanced. This cycle of observation and interpretation drives progress in astronomy. Each new discovery raises new questions. Those questions motivate new observations. The observations refine our theories. The refined theories predict new phenomena to search for. The red dots fit into this cycle. They answer questions about black hole growth while raising new ones about cocoon formation, jet launching, and the interplay between black holes and their environments. Future observations will address these questions, likely revealing additional surprises. In the broadest sense, the red dots change our understanding of reality by showing us that the universe's youth was more complex and energetic than we imagined. The story of cosmic evolution is richer and more nuanced than our theories suggested, and there is still much more to learn. The red dots are one discovery among many. Webb has been operational for just over 4 years. Its mission is planned to last at least 10, possibly 20, with careful management of fuel and systems. Decades of observations lie ahead. Each will add pieces to the cosmic puzzle. Some upcoming observations will focus on the red dots themselves. Detailed spectroscopy can reveal the composition of the cocoons, showing which elements are present and in what abundances. This tells us about the enrichment history of the gas. How many generations of stars lived and died before the black holes formed? Time series observations might catch variability in the red dot's brightness. Black hole accretion is not perfectly steady. It fluctuates on timescales from hours to years. Monitoring these fluctuations reveals details about accretion disk structure and stability. Webb will also search for red dots at different cosmic times. Do similar objects exist at 600 million years? 500 million? Pushing the observations earlier tests theories about when the first black holes formed. Finding them earlier than expected would indicate even more rapid formation mechanisms. Conversely, studying the transition from red dots to typical active galactic nuclei provides insight into cocoon dispersal and the evolution of black hole feeding modes. Webb can catch objects at various stages, from fully enshrouded to partially revealed to bare. Beyond black holes, Webb is revolutionizing exoplanet science. Its infrared instruments can analyze atmospheres of distant planets, searching for water vapor, carbon dioxide, methane, and potentially biosignature gases like oxygen produced by life. Every week brings new exoplanet observations. Rocky planets around cool stars, gas giants with unusual compositions, systems utterly unlike our own. The diversity of planetary systems challenges our theories of planet formation. Webb is also studying the first galaxies in unprecedented detail, not just their brightness and color, but their structure, star formation rates, and chemical compositions. These observations reveal how galaxies assembled from smaller building blocks and how star formation proceeded in the early universe. Star formation itself remains mysterious. We understand the broad outlines but not the details. How do molecular clouds fragment into stars? What determines the mass distribution of newborn stars? Why do some clouds form massive stars while others produce only low-mass ones? Webb's observations of nearby star-forming regions provide answers. The telescope is examining objects in our own solar system too: Jupiter's moons, Saturn's rings, Kuiper belt objects at the edge of planetary orbits, even comets and asteroids, fossils from the solar system's formation. Each observation refines our understanding of how planetary systems evolve. Supernovae, the explosive deaths of stars, are another target. Webb can observe them in infrared, seeing through dust that obscures visible light. This reveals the inner workings of these explosions and the elements they produce, which seed space with the raw materials for planets and life. Gravitational lensing, where massive galaxies bend light from more distant objects, creates natural magnification. Webb can use this cosmic magnification to study objects too faint to detect otherwise. Lensing has revealed some of the most distant galaxies ever observed, pushing back the frontier of cosmic exploration. Dark matter, though invisible, affects the distribution of normal matter through its gravity. Webb can map this distribution by studying how light bends around massive galaxy clusters. These observations constrain theories about what dark matter is and how it behaves. Each of these investigations contributes to a more complete picture of the universe. The red dots are important, but they are one piece of a much larger mosaic. Every observation adds detail, corrects misconceptions, and opens new questions. The history of astronomy teaches us that powerful new instruments always find surprises. Galileo's telescope revealed moons orbiting Jupiter, showing that not everything circles Earth. Hubble discovered the universe is expanding, transforming our understanding of cosmic evolution. Radio telescopes found pulsars, objects so strange their discovery was initially met with skepticism. Webb continues this tradition. The red dots were unexpected. What else lurks in the data, waiting to be recognized? What new classes of objects will emerge as scientists analyze more images? What phenomena will challenge our theories and force us to think differently about how the universe works? The next decades will bring answers. More deep fields covering more of the sky. Longer integration times revealing fainter objects. Better spectroscopy providing more detailed chemical information. Time domain observations catching transient events. Each year, our picture of the universe grows sharper. Each discovery, whether expected or surprising, adds to human knowledge. The red dots remind us that despite centuries of astronomical observation, we have barely begun to explore cosmic history. 13 billion years ago, black holes wrapped in fire glowed red across the darkness. Today, we see their light and understand what it means. Tomorrow, we will see even farther, even deeper, uncovering secrets that we cannot yet imagine. The universe is vast. Our understanding is growing. The journey of discovery continues, one observation at a time.